go to global options. Of course, I'm going to go to appearance. Then I'll change it to 125, I think so. Then apply that and see how it's going to look like. Let me see what the effect has it. Yeah, it has affected. Then I'll press escape for this to leave the scene. And so I'm just going to come here and drag this a little bit. And so here is where I simulated the data. I'm looking at soya beans. You know, we have different varieties of soya beans, and then we want to look at the genotypes which have been extracted from all the varieties. And then we want to use that one to cluster or to put together those varieties which are, related in some way. So that is what we are going to do. If you understand what cluster analysis is all about, clustering is like grouping items in terms of similarity. Those ones that are quite similar, their differences is not is quite minimal. Then we put that in one group. Then you do another one like that. Do another one like that, and it will be based on how you, the one who is doing your analysis, want to do this kind of grouping. And so let's simulate the data. So we have this, and so these are the genotypes. I decided to use the paste function to just create, let's say this is one of the genotypes. So I want this one, the genotype will end with, I think I should leave this, run that again, so that I'll have the first genotype will be 671. The next one will be 672 in that order, up to like 100 of them. And so that's what I've done. So if I print the genotypes, then you notice that I will have here. So these are the various genotypes of the different varieties that we have. And then in cluster analysis, you must make sure that you don't have repetition. If you have a genotype that has been repeated, you have to use the function called unique, and then you take those ones out, and then you're good to go. So we are looking at initiation of the first flower, how long it took for the first flower to initiate in each case. And then we are looking at days to 50% of flowers. See, so we also, and we are looking at the, the number of pores or something. So we can run that. Then we have the spade 7.5, the spade 7.5, 4.5 and 7.5. We have plant height, we have days to maturity, and then in that order. So seeds per pod, pores per plant, and then the yield, and then we're also looking at 100 seed weight. Yeah, some plants can have a lot of seeds, but the seed weight may vary. That what the agricultural people also put that into consideration a lot. So we've finished simulating the data. We're going to convert that into a data frame. And so I'm going to run this. That's going to give me my data frame. And so the data frame name is called soya. So if I pull this up, so you can see the genotypes are here. These are the first 6 lines, and you can see all the descriptions or whatever that we are looking at, which is here. So that's what, so I've already said that for you to be able to do your cluster analysis, what we are simply going to do is we are going to put these soya bean varieties, which are here. So these genotypes that which are here, a genotype represents one variety. So if we have a genotype which are here, so that's how we are going to group them. We are going to check all the genotypes here as against all the parameters or the metrics that we have taken, and then we are going to cluster them. So let's go ahead and then see how this, we just clear this here, and then we can go ahead and then see how we are going to do this analysis. So I will just go to pull this down a bit, pull this up a little bit. And also when we come here, you should know that we need a data frame to be able to do this. So we have our data frame, which is seated. So we just pick the first 2 lines. But remember that the first column is actually a character. For instance, if I should do, what is the structure? What is it? A structure of, okay. If I do the structure of soya, and then the structure of soya, so you notice that the first, the first variable, which is genotype, is actually a character. As you can see it here, it's a character. The rest are integers and numbers. So we have to take that one out. And so after taking that one out, we also need to standardize the data. So to avoid biases, so the standardization, we use scale. The scale will standardize the data automatically. So we are standardizing the data, which is called SOYA. So, sorry. So I'm going to have SOYA. So I have SOYA like this. And so the data itself is called SOYA. And then, but to standardize this means we're going to use scale function. So I'm going to have the scale function. Then I'll go there and say, I'm using the SOYA. But for the SOYA, we are selecting what the first rule, which will not be parts. Then we pack that into this called SOYA S. That's the scale SOYA data frame. So I'm just going to run that. And so this one will no longer have the first column, which is the genotypes. But we still want to leave the SOYA hanging because we will need it sometime to come. So we need to check for different distances. And so we use the distance function. So you can write this, you can just run the distance function and ask the question. And so it's a little bit slow. I mean, the network is quite poor here. So you see that it's taking a whole lot of time to be able to produce. So we can look at the distance function, which I think it ran, but I don't know why it is. Yeah, so we can have a look at the distance function very well. There isn't much information. So we have to first of all create the distribution, and then we pack that into what we call DS. That's going to be our distribution, or that is going to be our distances, sorry. So we use the distance function, and then we are using the scale so we have been one to be able to pack it into this variable. And so I'm just going to run that. And so we've created the distances. So we use the distance to be able to do that. Immediately you create the distances, you can see the distances are here. It's all right. This time around, I can produce a lot of things with this. So you can see how the distances look like. Maybe if I slide this a little bit, then I'll go up like this. So it has automatically created the distances between all the variables as you can see them. And so we can go ahead again. Maybe if you want to look at the distance options, you could run this, and then I don't really have much information there. So the first clustering we are going to use is the Kmeans. See, if you have your data sets, I just need this from somewhere. So we have clustering algorithm. We can have partitional clustering. We have hierarchical partitional clustering. You have something called Kmeans. It's one of the methods that is used in clustering. And apart from that, we also have the hierarchical, where we can use the other functions which are there. And so we are going to start with the Kmeans, which is here. The Kmeans is actually here. And so I'm not necessarily, let me pull this down. So with the Kmeans, all that we are going to do is we are going to say, I think I should change this name to reflect whatever I'm doing. So we are going to use the Kmeans, but in this case, we are using the SOYA. We have removed the first column and we have standardized. Then we use it with the Kmeans as a function, and then we run with it. So it will simply produce the Kmeans for us. And so the clustering has been done. So now, if the clustering is done, one of the ways to be able to know where the variables which have been created a clustering is to use the name function. And when you use the name function, then you put the Kmeans underscore SOYA clustering like this, and then you run it. So it's going to print all the variables which the clustering has produced. So we have a cluster, we have betweeners, we have center size, we have the tot SS, the ITAR, all of them, they have their meaning, or they have what they mean. So the most important one we are looking for is the cluster. So we can run this as our cluster, Kmeans underscore cluster, and then we select, once these are, we see all these variables here using the names function, it means we can use the dollar function to just pick, to select one of them, and then run that. And you can see that we have how many clusters? 2, because we selected 2 clusters around here. Now let me come back here and change it to, let's say, 5, and then run that again. And so if we come here and then we come and run this, you see that we're going to have 5 clusters. And then that's what we have. So we actually chose the clusters just the way we wanted. And so the next thing is we have to find the optimum number of clusters using the MB class. And what is it? And the MB class, if you want to use it, the optimal number of classes means, even though we have had all the classes, but what is the precise, or what is the ideal number of classes that we can actually generate from this particular data? You see, and so we are going to, that's what we mean by optimal number of clusters. So what do? We have to use this package called the factor extra, and it contains a function called MB class. So I have factor extra already loaded. Let me check if it is still loaded. And then I'm just going to come to this place and then check for factor extra. And then, yeah, it is loaded. So I don't have to load it any longer. So once it's loaded, this function, the FVS and then the soybeans underscore Kmeans method is we are going to use the WSS method to be able to make sure that we select the optimum. So we can run that. And that's going to produce this fine graph here. And then this graph is actually going to give us some kind of information of the optimum number of clusters. And to select the optimum number of clusters, we are always looking at the first bin. So why do we have the first bin? If you follow this line straight all the way down, the first bin is around here. To the best of my knowledge, this is where we can get the first bin. And how many classes are we talking about? 5. Well, maybe we can run another code and then see how that is going to look like. So we could also use the Silhouette argument. You see, instead of using the WSS, we can replace the WSS with Shiloh and then see how that is going to look like. That will produce a much more better graph, and that can. And so now come to look at that one. So you can see the clustering. So actually, the optimum number of clusters is 2. So you can see the first bin is around here, and then the maximum is actually 10 clusters, but the optimum number of clusters is actually 2. And that's what we have around here. Yeah. And so we can go ahead again. And what is the next thing that we need to find out? We have to find the number of clusters using the MB. That is also another method. This is maybe, I think I spelled this wrong. Right? This is just like another way of maybe doing it. So if you don't have this package called MB class, you can simply make sure that you install it. But I only have to load it, and then I just load it here. And I'm saying that I am going to use, the data is going to be Masoya, the scale data, and then this is going to be null. The distance will be Euclidean distances. The minimum is 2, and the maximum is supposed to be, what did I put there? I put 8. You can put any number that you want. And then the method is Kmeans, the index is all, and then the alpha is 0.1. You can put 0.2, any number. The alpha is always, what the bear is always telling us the intensity or the lightness of the plot you're going to generate. And so we can run that and then see what we're going to have. It's going to take a little while to generate this fine 2 plots for us to see. And then we can see again what is the clustering, the number of classes that we have. And then we can also see the number of classes, which is, so this is the index values. And then we also have here the second differences index values. If you want to know the meaning of this, what is it? I can do that for you. So this is another way that we do the clustering. Now, if we know that the optimum number of classes are 2, then we can set our K to 2 and then pack the values into this using the K-means function. So we go into the scale standardized data and we select the optimal number of classes, which is 2, and pack the whole thing, use the K-means and recluster that and pack it into, we have set K to here. So I'm going to run that, and then that is properly run. If you want, you can just print the K-means alone, and then you see this. It's the same thing that we have here. But if you go a little bit, you will see much more information. And it tells you that the K-means clustering with 2 clusters of size 52 and then 48. So this is the most important thing that you might be looking for. Then there are other values which are here. If you look at the initiation of flower, days of 50, number of flowers, then in that order, then it gives you all these the values that we are looking at. And so let me pull this a little bit down. And then now let's visualize the clusters. So now that we have set the K-means of the two clusters and we pack it into this, then we can go ahead and then plot the soya, and then we select the color, and then we go ahead and then say maybe we are looking at what the number of clusters. So this is already there. So this will take the original data, and so it takes a little while, but the plot is out. Let me try and see if I can zoom it for us to see how it's going to look like. So here, and so we can see this. You require a lot of time to be able to interpret this, but we can see the genotype here, and then we see this particular column all the way are the variables. You can also see another one over here. So the clustering, we have tried to have a visual impression of what it means. Now, that's one of the ways to. Now, let's also look at the hierarchical clustering. So how that one done is the same thing as the K-means clustering, but in the case of the method, you see, what is it? This particular code, if you look at it, is not too different from the one we have on top here. It's the same thing here. But this place where we have K-means, we are going to change it into what we call WD, word D. Now, let me pull this up and see whether I have the word D in hierarchical clustering in this particular small snip that I put. I'm unable to quickly glance through and see where it is, but I'm sure it's what it should be there somewhere. And so we just replace that, and then we run that. And of course, it's also going to generate some kind of plots. It's practically the same as the other one that we had. But here, you see, tell us that, so we can see our optimal number of clusters and then whatsoever. At this point, you may not be able to do much. So this is word D, but this is word D2. And so if you run that, it is going to be a bit different from the first one. And then just pull this up a little bit, and then you can see all these values which are here. Very important. According to the majority rule, the best number of clusters is 2. So this is what we are looking for, according to the majority rule. And then there are other indices that you may want to use. They propose 2 as the best number of clusters. Propose 3, the best number of clusters. So it will propose, but the first proposal is what you are supposed to work with. So we work with the first proposal, and then we are good to go. And so let me say this before we continue. It means, to the best of our knowledge, if we pick all those varieties, we can cluster them into 2. And so it means when we cluster them into 2, the 2, that is the best we can. It means the similarities and differences that exist amongst them, we can just put those ones into 2 groups. And that's all that I'm trying to put across there. And so I don't know what I assumed this for us to see, but if I had pulled this closer, you will see all that we are talking about here. And then I think this second plot always makes much more sense to me here. And then you are always looking at the bends, and then you're good to go. Now, with the second thing is, let's try and see whether we can build a cladogram that is going to look like evolutionary tree. The cladogram is, because we've already created the distances. Remember when I was talking about how to build phylogenetic tree or evolutionary tree, I spoke about the first thing: you have to have your data, you have to create your distance, you have to create your clusters, and then you can go ahead and then visualize it. So we created the distances, which is here. If you remember, we created the first time the data, we created the distances here. We use this particular function, the distance function, to create our package into DS. So we are now coming to build the cladogram, and we are going to use that same distance that we built earlier. And in this case, we are using the method of word.to, that's hierarchical, and then we pack it into this variable which we call word or something. I just don't know what I was writing there. So I've done that. And so now I can plot it, and then we can have a clearer view of what we've done. And so here we have our cladogram. That is not looking too sweet for me. Let me try and see if I can plot the second one. But for in this case, we are using an argument, which is called hang, and then we are subtracting 1. Yeah, so now we have the two, a plot which are here. We have the cladogram 1 and 2. What the difference is just this one is justified. It's like justified, like we have in Microsoft Word. This is not justified a little bit. But the levels and everything is the same. But for now, we can see it clearly. I will get to a point that I will explain how to make it clearer. And here, we can actually plot it with labels. And the labels, we are now going to use the genotype to label them. And so I'm going to come there. And so we simply have the genotypes here. And then, by the way it is the label, you can't see anything. But I will try and see. We can also use the rect.h class to be able to also plot it, and then we see how that is going to look like. And then this particular function rect.h class, it allows you to be able to divide your cluster, your clusters into the number of clusters that you have. And here, maybe before I run that, let me come here and run par through like this. And then I'm going to come here again and plot this so that it will cover the entire screen. And so let's have a look at it. And so look at what it looks like. Right? It doesn't look so beautiful according to my liking. So now let's plot the... And so now when we use the rect.h class, what it does is it's going to divide the clustering, which we have visualized it in a tree format, into the number that we want. So we selected 3, k equal to 3. So to divide it into 3. If we had selected a much more number, the clustering, it would have been more than that. If I selected k is equal to 5, we would have seen that the clustering will be like 5. And so we can see, and the color we chose is green. So this is 1, and then you choose another cluster here, choose another major cluster here. And so that is it. So if we had, and so we chose the color green. Here we are saying we are clustering, and the border is beginning from 2 to 5. And so this time around, the border is beginning from 2 to 5. So it's going to border into about 5 sections, and that's what we have here. Yeah, this is still not too visible because of the resolution that it comes with. And so we can also build this tree. We can also build this particular algorithm. So we're going to use the cat tree, and then we are going to go ahead and then, but cat tree comes with the R package called CLV. I do this, you can see it's going to give me all this number of classes, about 3 of them. And then I'm going to go ahead and then, the reason why I am doing this is that we have seen the clusters already, 3 clusters, 5 clusters, and the optimum is 2 clusters. So now, what is the next thing to do? We need to check how far is one cluster to the other. That is, in any case, the differences that exist between, for instance, if I say somebody is taller than the other, what is the height difference? That's what we want to look at. That's what we mean by the difference between one cluster to the other. How far is one from the other? How different is one from the other? So if I say somebody is heavier than the other, by what weight? So the weight by which you are heavier than the other person is the distance in this case. So we've created, we are using cat tree, and we are using this one that we have already. Remember, we built this one from the H class using the distance that we had already created, and we packed it into this variable. So that variable is what we are now using here with the cat tree, and pack it into HCM. And then the HCM I've already shown you, which is here. So now we can now check the intra and the inter-clustering distances using what we have built on top here. Okay, so I can come here and then library the CLV function package, and then that one is going to allow me to use this function called the cl.scatter.data to be able to visualize, or to be able to, for us to see the intra and the inter distance differences between the clusters and within clusters. So within clusters, we have different variables. And then between that variables, there are differences. How far is one variable from the other? And how far is the entire group different from the other group? That's what we mean by intra and inter distances. And this is how to be able to do that. So I'm now going to use this function, which is found in the CLV, and then use the scale data. And then I am going to set it together with the clusters. So it's going to go into the cluster we have already set, there are the Kmeans, and then to select only the clusters and then look at their differences. And that's all. And I'll pack it into the Kmeans here, because we also do the same thing for the hierarchical. This for the Kmeans. And so I'm going to come here and run that. So now when we print the whole clustering, this is what we can see: the inter and the intra. So you see, so we have the intra dot complete. So we can see what is it? The C1 and the C2, and then we can also see another intra here. We can go all the way. We can also see the clusters here, cluster 1. So these are the differences or the distances that we can see in all of them. Then the cluster distances, or the cluster side is 52 by 48, and then we can have the attribute class, and then in that order. Maybe you can read further for the explanations of this. I'm planning a different video where I'll be doing much more explanations of these plots, and then it will come very soon. So we can repeat the same thing here, but instead of now using the set K, we are now using the HCM that we just built momentarily, which is here. And so we can now run that one too, and then we can print the hierarchical inter and intra. So we can see the cluster.center. So we can see the here, and then this one, the distance here. And then we can see this and this, the distance is here. We can see this, and then this, the distance is here, then in that order. We can go here, and then we can also see the distances, and then how what the difference is, and how each work. Okay. So I think that's basically, and now if we want to find the cluster means using the aggregate function, so we want to find the mean of all the clusters. So we just run this, and then we can see that we have, in terms of like this particular variable, the the first day of initiation of flowers. This is, we can see the mean around there, the days of, you can see the mean, and then in that order. And so we can pick this particular one out as the data that we may want to look at, the different means of all the variables which we have used for the clustering. So basically, this is how what the clustering is being done. First of all, the data will have to be in the form of a data frame. All right. So we have our data frame here, which is Soya. What is the next thing to do? The next thing is to make sure you scale it. Scaling simply means use the scale function, but you cannot scale characters. So you take out any variable or any column that is character, or which is a string. Then you take those ones out. And that's why I have only one column, which is a character. So I took column 1 out, and then I scale it and I packed it into the scale Soya. The next thing to do is check for different distances. So you do that by just running this command, and then the next thing is to build your distances using the Soya bin data, the scale data. You build the distances and pack it into this variable called distance, because you will need it later. And so I think this one here itself, I can remove it. The next thing is to now do the clustering. So which particular method are you using? If you are using K-means, then you go for your K-means clustering. And remember, K-means clustering come under partitional clustering. So you are going to do partitioner clustering. You may use K-means, K-majors, K-modes, PAM, and then all this that I have here. So we are using K-means. And so what do? We just use the K-means as a function. Then we simply just put the the scale soybean data, and then we select the number of clusters we want. And that's all. Then we run that. Then we use the names function to be able to see the variables that K-means have built from this particular data in terms of the clustering. Then we can just select the one of the variable, which is a cluster, and then have a visual impression of it. Then we can go ahead and then find the optimum number of clusters using the fvis and mb cluster function. I mean, this particular function comes with a factor extra package. Then we run that using this method, WSS. We can repeat the same thing using this particular method called CLOG. And the same way, we can also find the number of clusters using the MB cluster function, which comes with the MB class package. You load it, you run this, and then you select this null distance, Euclidean distances. You can select the minimum number and then the maximum number of clusters. The method is K-means, and your index is all. You are putting all the data, and then we are saying that transparency or should be 0.1. Now, we can go ahead again and then use the K-means, because now after we've run this, we've noticed that the total or the optimum number of clusters are 2. So we use the 2 and pack and then run it with the soybean cluster again and then pack it into this. So we can now visualize it by just using the original soya, and then we want to color it based on what are the clusters. So each cluster will have a different color. And that's the reason why we did this. So we can also come and use the hierarchical clustering, and then we follow the same. Once we have already had this, which is a package and a function at the same time, we'll use that one. We'll select our data to the scale soya. The distance is Euclidean the same way, and then we can come here and choose WWAD. That's the method. Then we can use WWAD2, which is much more better than the first one. And then we run it. After that, we can build a cladogram. And the cladogram, if you know how to be able to do evolutionary trees, is very easy. So once we have already built the distances of the data, of the scale data, we can now use the H class. That's the hierarchical clustering, to be able to build our clustering using the WAD2 method and pack the whole thing to this variable. Then we can now come and then plot it, and we can have a visual impression. We can plot it again, but use an argument called hang is -1. Then we can use the same thing here, but this time I want to add labels to it. And then we are going to label using the genotype. Remember, the genotype was excluded, and that is why we had the soybean _s. But inside the soya itself, the genotype variable is still there. So that's why we kept it aside, and we use that one to be able to build it, to build the plot. Then we can use the rect.hierarchical clustering function to be able to make sure that we border each cluster. So each cluster will have a border. I choose the color green. You can choose any color you want. Or we can also use the same thing, the same function, but instead of choosing one particular color, we can say we want to color from 2 all the way to 5. It will automatically choose a color, and then cluster from, and then border it from cluster 2 all the way to 5. You could also change this number, the one that you want. Then here, we just decided to use the CATS tree, and then we built another small algorithm, and then put it in HTML, because we want to use it later. And then we come here, and then we have this package called CLB, because it allows, that package contains this function called the cls.scatter.data. This one, we use it to be able to find the intra and inter distances. And so that's what we did. We did that for the K-means. We did the same thing for the hierarchical clustering. And that is the reason why we're building this. Under the K-means, we use the set K, which we had already built, which was here. The set K, remember, here. We use the K-means because we had already seen that we were having some clustering, the number of clusters that we want optimum, which was 2, and we use that with the K-means function and build the set K. But when we got to the HCM, we decided to use the K, and we put the hierarchical clustering, the K to be 3. And then we pack that into this. We could have also used K to 2. And then we went ahead to, so when we come, we'll be using the set K here. But when we come to the hierarchical clustering, we won't use the set K because the set K is for K-means. Hierarchical clustering, we use the HCM, so as the hierarchical clustering mean. So we use that one, and then we also pack it here. That will allow us to see the intra and the inter-clustering distances. That's all I'm trying to emphasize. When we finish all these inter and intra-clustering distances, what are the average inter and inter-clustering distances? So we use the aggregate function to be able to do that. And then when we do that, we go into the, here we could have, so yeah, I had already used the data. I use it. That is why, what is it? And so we can, and we are going into the show here. We select, we take, anytime you see minus, it's me, we are not including. So we are taking out the first column, and we are going to a list. And so we pick this one, the clusters, and we are saying that go into each of the clusters and calculate the mean for us. And that's all. And so when we run that, we're going to have our, what is it? Work we have already run that, so which is here. So we can see the averages under each of the variable, the mean of each of the variable, then in that order. And that's all that we need to know about cluster analysis. This plot we have here, I don't know if it is visible enough. If it is not visible, now let me show you how to be able to make it clear for publication purposes. You see, it's not looking too good. So if you are going to export it,